let me start by recalling what we proved last time. So, a proper morphism and F is a torsion sheaf. And then, and finally, let S bar be a geometric point. And then, so we are interested in direct image of the constant sheaf, of a torsion sheaf F. So this is a sheaf on S, and I can compute its stock at geometric point, which is, I recall, under reasonable assumptions on F that it's separated of finite type. This is simply a homology, Qth homology of the scheme X tensor is spec or strict Henselization of S at this geometric point over spec or over S with coefficients in F. So, and now here we have the restriction map. So this is a local ring whose residue field is the residue field of S bar. So we have the restriction map to HQ of X S bar, where this is the fiber. And the main theorem from the last time was that this map is an isomorphism. So this is essentially always true under, again, reasonable assumptions on F, and this requires properness. So the picture to have in mind here is the following. So we have X, we have X over S, we have spectrum of this Henselization, strict Henselization, which maps here, and we have here a spectrum of the residue field of S bar. And so here I have XS, and here I have what is written here, X times over S spectrum of this Henselization. So we have this commutative Cartesian squares. So I think of this as a kind of tubular neighborhood of the special fiber, right? So I have, this is my S, this is a point, and this, here I have this fiber, X S bar, and think of this as a kind of cylindrical tubular neighborhood. And so you can take a sheaf F restricted to this cylindrical tubular neighborhood, you get this group. And on the other hand, you can restrict it to the central fiber, and you get this group. and the claim is that the restriction is always an isomorphism. So topologically, this would mean that this tubular neighborhood is is a deformation retract of the special fiber, or vice versa. So that's kind of the intuition behind this theorem. It has a, formally speaking, it's a generalization, but in fact, we saw that it's equivalent to the following base change property of derived direct image. So again, I have a map from X to S, which is proper. So proper. And I have any S prime mapping to S. And let's go with G. And so I can form the fiber product. And then, so for any F, we have a canonical map. So I can take F low star R, the derived direct image of F, and then I can pull it back to S prime. And there is for any F, and for any commutative diagram like this, there exists a map. You can, I call this G prime, and this is F prime. You can first take G prime inverse of F, and then F prime R F prime O star. So just the adjunction properties imply the existence of such canonical arrow, and the claim is that if F is proper, then this is an isomorphism. Okay? Да. Потому что у нас есть отображение, а значит проверить, что это изоморфизм, достаточно на слоях, и тогда это редуцируется к тому утверждению. С другой стороны, если в качестве S штрих взять геометрическую точку, то получится это утверждение. So as one of the homework problems, the easiest homework problem, asserts, so an immediate corollary of this formulation is that homology, a type homology of a proper scheme over an algebraically closed field does not change if you take any extension of the base field, which is also algebraically closed. This is something that is not true for non-proper schemes, as we saw in the case of A1 over a finite field, over algebraically closed finite field. Okay? So this is a deep fact that we...
I have a question. So
yes.
One of the vague conjectures we originally discussed was that if we define cohomology over finite field, then if a variety comes from characteristic zeros and the petty numbers in characteristic A and 0 agree, is this like from this fact? Or is
No. It requires, it's something else.
And if you assume that F is flat?
What is true is that if you if you say have a variety over ZP over periodic integers, and F is a, say, constant sheaf with coefficients, L power n torsion sheaf, where a constant sheaf such that P is invertible in this sheaf, and if you have a smooth proper scheme over ZP, then the Tal homology of the geometric generic point is equal to the Tal homology of the geometric closed fiber.
But this theorem doesn't help.
This doesn't help. That's something else. This is called smooth base change theory. Well, okay, so now I want to discuss some applications and one application will be so one is homology with compact support. Compact support. Okay, so here is a construction. So suppose I have a scheme X over a field separated finite type. So I want, and I have a sheaf F torsion sheaf. And then, there exists, so I want to define for you what is homology of X with coefficients in F with compact support. So the construction depends on some auxiliary choice. Namely, I have to choose a compactification of X, namely an open embedding to a scheme X bar, which is, this is open, and X bar is proper over spec K. So this is proper. So the existence of such a compactification, it's known to exist for any X, and this is a theorem of Nagata, which is, which is technical and, well, not particularly easy, but in practice, so for example, if X is quasi-projective, you just embed it into a projective space and then take the closure, right? So in practice, constructing such X bar is something very simple. So, and I think that Nagata's proof was written in old language, so it was rewritten by, well, it was reproven by Deligne and then written down by Conrad. So there is a relatively short exposition of this. So, well, this bar, of course, is not unique. You can take X bar and take any, say, blow up of X bar at a point which is not in X and still get another compactification, right? You can take embedding of A2 into P1 times P1 or in P2. So now, so I define homology. Да. Значит, что все слои, это абелевые группы, они убиваются, каждый элемент убивается умножением на какое-то целое число ненулевое. Вот. Okay, so homology with compact support of F is defined to be homology of usual homology of X bar with coefficients in J low star, low shik of F. Нет, совершенно не предполагается. Да. So what this definition, well, so homology with compact support is defined in terms of the usual homology of this new sheaf, right? So we define this functor as right adjoint to the restriction functor for any étale morphism, in particular for an open embedding. So this is a sheaf on x bar whose stocks at every point of x bar, which is not at x, is 0, and whose restriction to x is your original sheaf, right? So it's also called, in this situation, extension by 0. So, of course, for this definition really to make sense, you have to show that this does not depend on the choice of compactification, right? I could take embedding of x into anything, and I could produce some operation, right? I could maybe replace, write something like this with replacing j by j, by some other sheaf. So really the content of this is that this construction does not depend on the choice of compactification. It would depend if I put star here, for example. Okay? So claim H, this compact support, is well defined, meaning that it does not depend on the choice of compactification. So let's give a proof. So suppose I have two compactifications of, right? So I have x, and I have x1 bar, and I have x2 bar. And I want to compare these groups. Okay, I need a 2 to compare it. So this is my J1. This is going to be J2. So these are open embeddings. And in this situation, I can produce a third compactification by first taking the product of these guys, which is also a proper scheme. And then I have a diagonal map from x to this, right? And I can take, right, so I have this arrow. And, that's, the image here is not open, but so I can, what I can do, I can take the closure of x here. And let's call this closure x3 bar, right? This is the closure of x in x1 bar times x2 bar. So then by construction, we have this factorization, this is a closed embedding, and this is open. So starting with two compactifications, I produced a third compactification. And because this scheme projects to x1 bar and x2 bar, I can restrict this projection, so I have this commutative diagram. This has the projection maps. So I want to show that these two groups for x bar 1 and x bar 2 are the same. And by transitivity, it suffices to show, to construct an isomorphism for these two compactifications and for these two compactifications, right? So therefore, these two compactifications are particularly nice in the sense that one maps to the other. So therefore, the proof in general is reduced to the following. So we may assume that So when proving this theorem, the claim, we may assume that we have the following situation. We have x mapping to x1 bar, and we have another compactification. But in addition to this is still J1 and this is J2. In addition to this, we have this map, which is automatically proper, which makes this diagram commutative. So I can assume the existence of this map P, because it exists here. Right? So, and now we have the following lemma, which implies the claim. So let's take J1 lower sheik of F, and let's take its P low star of this. Okay, maybe I will write it as follows. So let's take R P low star of this. So my claim is that what you get is J2 lower sheik of F. Right? So clearly this implies, so a priori, when I apply this derived direct image, I get a complex. So the first assertion is that this complex has homology only in one degree. And in this degree, it's what's written here, right? Higher derived direct images vanish. And so why that? Well, first of all, clearly this statement implies a claim, right? Because this you want to compare these two groups. So if you consider homology, if you want to compute homology of x1 bar with coefficients in this sheaf, you can do it as follows using our Larrey spectral sequence formalism. You can first take the derived direct image here, right? That's what we have here. And then you need to take homology of x2 bar with coefficients in this derived direct image. That will give you, so explain it. So H Q of x1 bar with coefficients in J1 sheik of F is the same as R Q gamma of x2 bar with coefficients in R P low star of J1 sheik F, right? Не, это формальность. Просто потому что у меня есть любой пучок, у меня есть пучки на x1, у меня есть функтор пучки на x2, и отсюда есть функтор Вабелевой группы, в которой есть глобальные сечения. И всегда, значит, композиция этих функторов — это тоже глобальные сечения. Значит, это отсюда следует, что функтор R гамма. Да. Угу. Так что. Да. Нет, но слева стоит комплекс пучков. Справа стоит просто пучок. Но когда я говорю, что что-то равно, это означает, что это квазизоморфные эти комплексы. То есть этот комплекс, в частности, утверждается следующее. Эквивалентная переформулировка, что если я здесь напишу высшие прямые образы RQ, то они будут равны нулю при Q больше нуля, а при Q равном нуля будет получится вот это. Ага. Вот. Поэтому просто сюда вот вы подставляете вот эту форму и получаете то, что нужно. Окей. Да. Да, так вот теперь утверждение леммы. Well, so just use base change. Use proper base change. Okay, so how you use it? So first of all, if you take this guy and restrict it to x, x is an open subset in x2. Nothing changes because over x, this map is an isomorphism, right? Ну, значит, вот да, вот если я вот этот пучок, я ограничу его на x, вот этот комплекс пучков, ограничу его на x, то ничего не, то получится просто f. Значит, по функториальности, по сопряженности у меня есть отображение из we have a map from this guy to this guy. Okay? Just because constructing such a map is equivalent to constructing a map from f to the restriction of this to x. And we agreed that the restriction of this guy to x is f itself. So all I need to check is that this map is an isomorphism on stocks. Right? So, so this is definitely an isomorphism at any point of x2 bar, which is in x, because over x, the two sheaves are just f. So if x is, if s bar is not is a point of x to minus x, if it's in the complement, let's compute the stalk at this point, which is in the complement. So here I have J2 Lorschik of F, and I computed the stalk at this point. What do I get? 0. Right? Because that's the extension by 0. So what do we get here? So we need to check that this is an isomorphism. So we want to check that this R P low star of J1 Lorschik of F is also 0. Right? But that's, this is by the proper base change theorem, right? By the first formulation of the proper base change theorem, this is simply homology R gamma of the fiber, right? Let's say P inverse of S bar. That means the fiber product. So I have a point S bar here, and call the fiber P inverse of S bar. Maybe I'm using some notation. That's the fiber. Right? With coefficients in this sheaf restricted to the fiber. Right? But look, so this fiber, right, does not intersect X. By construction. And my sheaf, restricted to any point in the complement to X, is 0, because this is low sheaf extension. So this is just 0 sheaf. So computing cohomology of 0 sheaf is easy. You get 0. So really the content of this lemma is this isomorphism here, which is the proper base change. If you replace the fiber by its tubular neighborhood, the tubular neighborhood can intersect X, right? It's an open neighborhood at the end of the special fiber, of the fiber. So, okay. So we proved the lemma. So we constructed a map. We showed that for any geometric point of X, well, this is an isomorphism tautologically, and we proved that for any geometric point which is in the complement, the Stokes are 0. Right. Good. So this proves that cohomology with compact support is well defined. And so here is a generalization, straightforward generalization of this. So more generally, we can define the direct image with compact support, generally. So let X over S be a separated morphism, of finite type. S is Noetherian. Then there is a generalization of Nagata theorem, also proven by Nagata and reproven by Deligne. Then there exists a relative compactification of X. So you can construct J, which is open, X bar, and such that this map is proper. So let's call this F, and this will be F bar. So again, in general, that's kind of could be challenging to prove, but in the case when F is quasi-projective, you can take closure in projective space. So constructing X bar is not complicated. And then, so we define R J low chic. So, and this is not kind of, this is just in separated letters in the sense that that's not a derived functor of something. We define for any torsion sheaf. Yeah, did I say that F is torsion? Right. So F torsion. I use this because the proper best change theorem holds only for torsion sheaves. So we define this to be, there's F, yeah, that's what I want to define, right? I want to define a sheaf on S. So again, if for a Thal morphism, we have a definition of direct this F low chic. It was a joint functor, and it was exact. So here, F is not assumed to be tal, it could be dimension of the fibers could be positive. So by definition, this is J low sig of F, and then I take R F low star, F bar low star. Right? So if S is a spectrum of a field, you recover the definition that we had before. Spectrum. Yes. Если F гладкий, получается ли это как производный? Ну, сейчас. Ну, а что такое F с факториальчиком? И для этальных. Для этальных. Да, нет, если F этально, то тогда функтор, вот этот он точный, производный от него брать не нужно, получится то же самое. Okay. So, and again, there is a claim. Proof is completely analogous to what we did in the case of a point. So I do not repeat it. This is well defined. So this is very good. So, well, by construction, so if X is proper, right, then homology with compact support of any sheaf on X is the same as usual homology, right? Because you can take for X bar just X. And similarly, if this map happens to be proper, then you can take for X bar X and you recover the usual derived direct image. So for proper maps, these two functors coincide tautologically. Now, so what we как является, значит, я мог бы вот сначала определить такой функтор, стерев здесь R. Ну почему? Я могу вот так вот определить? Пожалуйста. В чем проблема? Получится какой-то функтор. Он будет, конечно, не точный, он будет точным слева, потому что этот функтор точный слева, этот точный. И потом я бы мог у него взять правый производный. Значит, ну, вопрос, правда ли, что этот правый производный будет вот такой вот. Здесь мы делаем другое. Да? Мы берем сначала прямой образ с факториальчиком, а потом применяем вот этот производный функтор. Можно спросить, значит, там всегда будет отображение из одного в другое, а именно будет отображение из производного от этого вот в эту композицию. И это был бы изоморфизм, если бы вот этот вот функтор, вот этот, переводил бы инъективные объекты в инъективные. Но это не так. Поэтому, вообще говоря, это не изоморфизм. Вот. И определять следует вот так. Okay, so no, here is an easy claim, which is an immediate corollary of base change, proper base change. So for any R, if you take any torsion sheaf and compute the stock of this derived direct image with compact support at any point, then this is the same as cohomology with compact support of x s with coefficients in f. So why that? This is an immediate application of the proper base change theorem applied to this morphism. Oh, yeah, with compact support. Thank you. Because the restriction of this sheaf to a fiber of this morphism is, well, it's zero extension of the sheaf F restricted to the fiber of this morphism. Okay? And more generally, so if you have a base change property, now it holds for any morphism, well, under the assumptions that it's separated finite type. So here you can form the... Вот это, да, доказали. А именно мы просто применили, ну да, давайте его докажем, если хотите. Значит, что получится? Значит, вот определение, значит, мне нужно посчитать будет когомология слоя x с чертой s с коэффициентами вот в этом пучке. Но вот эта штука — это компенсификация вот этого. Так что это определение. А вот это теорема о собственной замене базы. Okay, and consequently, we have a generalization of this. So if this is any Cartesian square, this is G, this is G prime, this is F prime, then for any torsion sheaf, you can do the derived direct image with compact support. Then you can apply G inverse. And this is isomorphic to G prime inverse of F. And then you take R F prime with compact support. So if you replace one of the functors, low star functor, by the direct image with compact support, the proper base change theorem holds without properness assumption. That's the moral, right? When F is proper, you recover the statement, the usual formulation. But there is not really more content in this. Though, as we see in a second, this is very convenient to have well, these functors and the proper base change in this generality. Okay, so here is how we are going to use it. I will give you a sample. Suppose, so let's prove theorem. Suppose I have, so let's assume that dimension of the fibers of a morphism from X to S, which is assumed to be nice, so finite type and separated. This is F. Less, well, less or equal than some integer n. Then for any torsion sheaf F, RQ F low star of F is equal to 0 when Q is greater than 2n. Okay? So here is a corollary. So suppose I have X over K equal to K bar over an algebraically closed field. Suppose that it's proper, then HQ of X with coefficients in any torsion sheaf, usual homology, is 0 when Q is greater than twice dimension of X. And this is a very nice statement, right? So it's well known in topology that if you have a topological space of dimension 2n, then homology of topological space, well, in classical topology, that definitely holds, right? And so we have it for a Tal homology, which is great. So first of all, why this is a corollary? So if S is the spectrum of the algebraically closed field, then, well, this derived direct image is the same as homology, right? Sheaves on the spectrum of algebraically closed field is just a billion groups, and the factor is direct image is global sections. So so because the map is proper, F low chic is the same as F low star, so we get this statement. And if without properness assumption, the same is true if you replace usual homology by homology with compact support. Okay, so by the way, that's in fact it's true even for usual homology, but it requires more work. So let's give a proof, because it's really, remember that we did some computations for curves. For curves, when X is a curve, we proved this statement. It was a kind of, we used some diversage. We reduced to, first we reduced to the case when F is a local system, and then we use the Traith method to reduce to take some finite cover of this curve and then reduce to constant sheaves on a curve. So this was we know this in dimension 1. And the nice thing about this, the power of all this formalism and proper base change essentially is that you can prove many things about higher dimensional varieties by reducing the statement to the case of curves. Here is how it works. So, okay. So, so first of all, without loss of generality, we may assume that S is spectrum of a field, right? Because even algebraically closed field, because what we want to prove is that the stocks at every point, geometric point of this guy is 0. And by this proper base change by the base change for this F low chic, it's the same as computing homology with compact support of the fibers. So we may assume this. And now, so I take X, now I will do it by induction on dimension of x. So I take x and I take some affine open. Well, this is affine. In x, which is well, dense affine open. And so here I have the closure, the complement, which is x minus u, and let's call it z. And this is I. And then for any sheaf f, I have an exact sequence. I can restrict f to u and take, this is j, j over sheaf of this. That's the extension by 0, and it maps by junction to f. And the complement, well, so this is an isomorphism on u, right? And so this is going to be a sheaf supported at z, and its stalk at every point is the stalk of f, because the stalk of this guy at every point of z is 0. Right? So this is just I-O star of f restricted to z. Yes, so this is a short exact sequence. So now let's recall that cohomology of cohomology, this compact support of x with coefficients in. Да. Но я сначала его ограничил сюда, а потом взял прямой образ. Это будет такой пучок, который совпадает с f на z, а в везде остальных местах 0. А этот наоборот. This cohomology, well, this is a closet embedding that's in particular a proper map. This cohomology is the same as cohomology with compact support of z with coefficients in this. So now z has smaller dimension. I assume that U is dense. Oh. So we know the result. We know the vanishing for these groups. We know that they vanish when Q is large enough, right? 2n minus 1 at least, and greater. So from the long exact sequence, it suffices to show the vanishing for this sheaf. So similar cohomology with compact support of x with coefficients in here is the same as cohomology with compact support of u, f restricted to u, right? So we reduce to showing vanishing of these groups, right, when Q is large enough, greater than twice dimension of U. And so here, it's very easy to so U is affine. And it's easy to fibrate in curves. You could do it in general, but it would require some maybe blow-ups, a bit of extra work. But for affine X, it's particularly simple. So the first result in commutative algebra, the most useful result for application in algebraic geometry is Noether normalization lemma. So there exists a finite surjective map. Finite surjective. Map to the affine space, to an affine space. And, okay, so now I will consider projections. And I'll give some names to these projections. So this will be pi n, and this will be pi n minus 1, and so on. So, and let's call this map G. So then, R G low chic of so R gamma, let's see, so R, and that's composition, is F. So R F low star, low chic of F is composition. So you take R G low chic of F, then you take R, what am I saying? Yeah, pi n lower chic, then so on, R pi 1 lower chic. Yeah. So we want to show this is homology, this computes homology with compact support. K is algebraically closed. And we want to show vanishing of this in higher degrees. But now let's see what we have here. So R J lower chic of F. Well, G is finite, in particular it's proper. So this is just the usual derived direct image. And because G is finite, there are no higher derived direct images. This is just a G low star of F. So it's supported in 1 degree. So now R pi n low star of this guy is supported, and it's a complex in degrees 0, 1, and 2. Right? Why that? Because so the fibers of this morphism are curves, namely the A1. So by proper base change, so I want to show, for example, the vanishing of the third cohomology sheaf of this. Third cohomology. So that's the same as cohomology with compact support of the fiber. So I take this sheaf, I restrict it to a fiber of this morphism, geometric fiber of this morphism, and compute cohomology with compact support. But the fiber of this morphism is a curve. So I'm computing cohomology of P1 with coefficients in some sheaf, 0 extension of this guy. And we already know the vanishing, right? We know that for curves, homology may exist only in degrees 0, 1, and 2. So we conclude that this holds. Now, similarly, if you now consider this, and you apply it to this complex, right? R pi n worship of G low star of F, you get is supported. In degrees 0, 1, and 2. 3, sorry, and 4. Right? So how you get this? So if this were just a sheaf, so supported in degree 0, you would get that this derived direct image is supported in degree 0, 1, and 2. But now, so any complex has a filtration whose associate graded is homology sheaves, shifted in appropriate degrees. So you get it by one exact sequences. Okay? Все. Да, да. Ну и вот как бы тот факт, что мы можем, вот собственная замена базы, которая здесь очень используется. Ну вот здесь для таких функторов она, собственность не нужна, но вот как бы замена базы. Мы используем то, что слои прямого образа, это то же самое, что когомология слоев. Так это работает. Very good. So here is another result which is proven using the same technique.
How do you know that the composition of the maps?
Very good question. So you need to work a little bit to apply Nagata's theorem of times, so to construct appropriate, compatible. So the question is why we have this formula, right?
So you have to interchange J over shrink with R and F stars somehow.
Yes. So you need to use proper base change again. So that's a good question, but it's formal. Once you have once you choose appropriate compactifications. So you have X, you have U, you have AN, you need to choose compactification such that they all maps to one to another. And then it's formal using base change. And the existence of such nice compactifications again follow from Nagata theory. Follows from. Okay, so here is another. So we prove the result on homological dimension of schemes. And so here is another result, which is proven using similar technique. So if F is finite constructible, well, again, so I recall what finite constructible means. It means that there exists a stratification, a finite stratification of, so X is a union of locally closed subsets such that F is restricted to HXI is a local system of finite abelian groups. of finite groups. Right? That's the definition of constructibility. So an example of a constructible sheaf is you can take a local system. Yeah, that's a constructible sheaf. You can take its F low star extension, zero extension, for example. That's a very good example. So if F is finite constructible, then and you have any morphism, reasonable morphism of finite type, as before, finite type and separated. Finite type, separated, as Noetherian. As a matter of fact, we defined this notion of constructibility only for Noetherian schemes. Then RQ, F lower sheik of F is constructible. Well, corollary of this is that if K is, if you have any scheme, separated scheme of finite type of an algebraically closed field, then homology with compact support with coefficients in a constructible sheaf is finite. So the previous theorem assures that no, just as orders. Dimensions over what? This is not a sheaf of vector spaces. Yes. So what the previous theorem assures that these groups exist only in finitely many degrees, right? When Q is greater than twice dimension of X, this group is 0. Now, this theorem assures that when F is not big, right? For example, a local system of finite abelian groups, then these groups are also finite, which is a very good result. I will not, which is very good, but I will not prove it. So the idea is to use a similar strategy. So you reduce it to the case of when X is affine. You may use Noether normalization as here. And then, that's still OK. And this is constructible because this is a finite morphism. You can find the stratification over which it's a tall. This is constructible. And then you need to show that if you take the direct image of a constructible sheaf under a morphism whose fibers are smooth curves, then it remains constructible. So we already know that Stokes are finite, right? Finite, because we know that homology of a finite constructible sheaf on a curve. We know this statement for curves. So using base change, we know that the Stokes of this guy are finite abelian groups. But you need to work a little bit more. You need to show that, for example, there exists a dense open subset over which this is a local system. The Stokes do not jump. So I will omit this part of the argument. OK. So our goal is to prove Weyl conjectures. And so the first Weyl conjecture is about rationality of zeta function. And so we already discussed the strategy. We want to have Lefschetz formula for the Frobenius acting on algebraic variety over a finite field. And we want to use, we want to compute the number of FQ points as alternated sum of traces of the Frobenius. And just the very existence of this formula will imply the rationality of zeta function. But in order, well, the number of points is an integer. So we need to have a homology theory with coefficients in a field of characteristic 0, right? So if you, like, say, consider homology with Z mod LZ coefficients, all you can get as sum of traces is a number in finite field, FL, right? So you can compute the number maybe of points modulo L, but that's not good enough. We want actual number.
Why is just picking L extremely large as an option?
That's a good question, but you see, we need to apply the Lefschetz formula not only for one particular field, FL, but also for FL squared, FL cubed, and so on and so forth. And so that's not. So we really want, but that's kind of an idea. So we want to put pick L very large, but you have to kind of do some work here. So ZL sheaves, oh, I will not say much today, I will continue next time, sheaves. Well, that's the next subject. So here is an exercise. So again, suppose you want to define homology with coefficients in something of characteristic 0. So here is an exercise. Suppose X is normal. Then a tall homology of X with coefficients in a constant sheaf. This is a constant sheaf. So what is it? I want to express it in terms of the fundamental group. Hom. These are just continuous homomorphisms from the tall fundamental group of X into this abelian group. And when I say continuous, I really mean that, well, this is a topological group, and this is a discrete group, right? So that means that saying that it's continuous means that it factors through a finite quotient, right? That's equivalent. So, well, we observed this, and this long time ago, that this holds when lambda is a finite abelian group. And you do not need even normality assumption here. Well, this group classifies torsors, right? So when lambda is a finite group, so you classify torsors over fine group, right? Lambda is discrete group. It's finite. It's a fine variety, so these torsors are exactly in one-to-one correspondence with this homomorphism. Lambda is commutative, also abelian. So, so you need a little bit more work to show that this also holds if X is normal for any lambda. Okay, this is a good exercise. It's not completely trivial, and it's not hold if X is something like this. In particular, so if lambda is torsion free, then H1 et al. Of X with coefficients in lambda is 0. Right? Why that? Because, as we already observed, any continuous homomorphism factors through a finite quotient. But there are no homomorphisms from a finite group to a torsion-free group. So this is a drawback. So you can't really define homology with integer coefficients, reasonable homology theory, right? It would give you 0. So my time is over, so let me just give you one exercise, which will not be used, but still it's a nice exercise. So let's take a cubic with double point. This is X. And this is P1. So it's a cubic, right? So it's a rational curve with a single double point. And then if you compute a Talha homology, first a Talha homology of X, and it's over algebraically closed field with coefficients in Z. What do you get? According to this result, you should get 0. But that's not true. In fact, it's Z. And it's a sort of a reflection. Well, you know that this classifies, let me convince you that this is Z. So this group classifies torsors, Z torsors over X. And I will give you an example of a Z torsor. So let's take this infinite chain of P1. Right? Infinite chain of P1. It's a tree. And so there is an action of the group of integers, right, on this infinite chain of P1, just by translation. And if you take the quotient by this action, you get this. So this is an example of a Z torsor. Convince yourself that it's locally trivial for a Tal topology. So this shows that ну да, абсолютно верно. Окей.
А если мы разрешаем только конечные этальные в нашем определении этального степени, там...
Ну так мы же разрешаем только конечные. В смысле, имеете в виду конечные или квазиконечные? Ну, у нас разрешены только квазиконечные.
Ну, вот эта картинка, она вроде бесконечная.
Ну и что? Я могу покрыть, сейчас, как это хорошо сказать. Но дело в том, что этот торсер, он становится тривиальным. Вот давайте я, может быть, сделаю это вот так. Вот пусть у меня, чтобы было еще проще. Давайте я рассмотрю вот вместо такой картинки вот такую. Это две копии по этим. Тогда я утверждаю, что даже когомологии Зарисского равны Z. Постоянного пучка на такой схеме. Ну и что? И вот, собственно, Вот, собственно, торсер. Я утверждаю, что он локально тривиален с топологией Зарисского. Ну, а именно, если я выброшу эту точку, он будет тривиален. Если я выброшу эту точку, он тоже будет тривиален. У него просто будет сечение. И тут нет никакого противоречия. То есть, да, этот торсер, чтобы его реализовать, не нужно переходить к бесконечным этальным накрытиям. Достаточно перейти просто к покрытиям Зарисского. Они очень даже конечны. Ну, а чтобы реализовать тот торсер, там надо взять сначала двулистное накрытие, получится вот такая картинка, а потом выбрасывать эту точку и тогда реализуется тот торсер. Вот. Ну, а чтобы решить вот эту задачу, нужно использовать такой факт, что если у вас есть на нормальной схеме торсер над дискретной группой, если он в общей точке тривиален, то он тривиален и везде. Это простое утверждение. Вот. Ну а в общей точке вы как-то это сводится к гомологии МГЛА, но к гомологии ГЛА, к гомологии проконечной группы это всегда непрерывное отображение из этой группы в поле первой когомологии в группу коэффициентов. Но там же нужно, чтобы значит, какое свойство нормализации здесь используется. Значит, давайте, вот как бы ключевое место здесь такое. Вот у вас есть x, и в нем есть открытое множество u. Вот когда вот эту задачу решаете, давайте обозначим это вложение g. Тогда вот то, что нужно знать, это такое, что вот это вот продолжение постоянного пучка — это постоянный пучок. Вот такое утверждение используется. И зная это утверждение, формально получается, что любой торсер, который на u тривиален, любой торсер на x, который тривиален на u, также тривиален и на x. Ну а что же здесь вот написано? Вот в этой картинке это неверно даже для топологии Зарисского. Если вы возьмете постоянный пучок на дополнение к этим двум точкам и продолжите их, что получится? Что будет, если вы рассмотрите вот такую картинку, вот выкинете эту точку, возьмете постоянный пучок на дополнение, а потом продолжите? Да. Вот это то, что мы не хотим. Здесь, вот в этой картинке, если вы в топологии Зарисского делаете, то, значит, как бы что такое вообще, как вы считаете продолжение? Вы должны эту точку вот выбросить и рассмотреть глобальные сечения на окрестности. Но в топологии Зарисского это не очень хорошая картинка, эта штука все равно будет связана. Если вы из любое возьмете открытое множество, выбросите из него эту точку, у вас все равно будет связанная штука, потому что у вас схема неприводима. Но в этальной топологии нам нужно рассматривать такие этальные накрытия. И этальные накрытия, они уже могут быть у этой схемы приводимы. Потому что, вот, например, одно из этальных накрытий, оно вот такое. И тут эта схема уже приводима. Когда вы там будете брать прямой образ, у вас получится побольше. В общем, как бы вот то, что используется, это то, что любое этальное накрытие x является, ну пусть x связано, то тогда любое этальное накрытие x является неприводимым. Любое связанное этальное накрытие x является неприводимым. Я не знаю, как это сказать. Но, значит, если у вас есть связанная нормальная схема, то она автоматически неприводима. Если у вас есть нормальная схема, ее над ней этальный морфизм. Если x нормально, то и этальный морфизм тоже нормален. Поэтому, в частности, если он связан, то он неприводим. Вот. Хорошо. Давайте.
У нас еще чего нам еще не хватает, чтобы доказать гипотезы Вейля из теории? У нас все готово?
Ну, значит, что мы завтра будем обсуждать? Мы будем обсуждать пучки, которые, строго говоря, пучками не являются, но мы как бы так руками определим когомологии с коэффициентами в чем-то характеристики z 0, а именно мы возьмем когомологию с коэффициентами в z по степени nz и перейдем к пределу. Вот. Дальше мы, значит, у нас получится когомология с коэффициентами в эллиптических числах. И для таких когомологий и для Фробениуса мы докажем формулу Левшица. Докажем мы ее, причем как бы с коэффициентами даже не с постоянными коэффициентами, а с любыми, с коэффициентами в любом конструктивном пучке. И, собственно, доказательство, оно как бы происходит редукция к кривым, и там очень важно, что пучок любой. Вот. И этого нам будет достаточно, чтобы доказать, значит, гипотезу про рациональность. А гипотезу, которая Римана, мы, ну, я сейчас очень просто короткое ее доказательство, ну, я не, с другой стороны, как бы объяснить, что там, в чем там идея, ну, проще его рассказать, чем как-то комментировать. В общем, у нас все есть пока для когомологии с постоянными, с конечными коэффициентами. Вот наша как бы ближайшая цель это будет ну, как бы какой-то час теории перенести на такие вот пределы.
Еще есть функциональное уравнение, которое, по идее, соответствует двойственности Пуанкаре.
Да, двойственность Пуанкаре, значит, я ее собираюсь в качестве разбить на несколько задач, это будет в следующем домашнем задании для кривых, но с любыми коэффициентами. Нет, формула Левшица для гладких компактных многообразий. Ну, как бы вот формулу Левшица с постоянными коэффициентами для гладких компактных многообразий можно выводить из двойственности Пуанкаре. Но в доказательстве гипотезы как бы Римана там нужна формула Левшица не с постоянными коэффициентами. И она не следует из двойственности Пуанкаре. С другой стороны, она немедленно, как бы, общее доказательство сводится к кривым. Но там есть как бы некоторое замечательное дополнительное рассуждение для пучков. В общем, то, что мы будем обсуждать на этой неделе, то есть четверг и на следующий, это формулу Левшица с непостоянными коэффициентами, но для кривых. Мы ее выведем из формулы Левшица с постоянными коэффициентами для кривых. Вот. Да. И значит, отсюда с помощью теоремы о собственной замене базы формально получается формула Левшица с непостоянными коэффициентами для любого многообразия. Это я тоже объясню. Ну вот, это, я думаю, что это займет, значит, эту вот четверг и еще следующую неделю. Ну а последнюю неделю, я не знаю, когда у нас официально должны все заканчивается, но вот чтобы... ну хорошо, хорошо. Ну, я не знаю, в общем, там будут какие-то защиты, надо, расписания еще нет. В общем, я думаю, ожидаю, что мне нужно вот 2,5 недели, чтобы, значит, доказать рациональность и гипотезу Римана, как бы, ну вот ту, которую Делинь доказал.
А то, что числа по этих характеристикам,
0 это я не, ну, то есть если как бы это не входит в эти 2,5 недели, это требует некоторой отдельной работы, которая тоже очень интересна. Но если останется время, то есть останется у вас желание, то тогда и про это поговорим.